Good day, everyone. Welcome to Lubrication Experts. My name is obviously Rafe, and today I'm here with Willie Gartner from King Industries, and we are at the home of Alkylated Naphthalenes. Now, if you have been listening to this podcast for any stretch of time, or you've seen the YouTube channel, you'll know that Alkylated Naphthalenes are my favorite base oil, as much as anyone can be said to have a favorite base oil. That's probably the nerdiest thing that anyone's ever said in this industry. So, you know, being that we're at the home of King, I'm up here actually for a visit. We don't get to do these interviews in person very often. So, Willie, you get to be a special guest, right?
Real special.
You get the in-person experience.
Just so you know, Alkylated Naphthalenes are my favorite base oil too.
Oh, excellent, excellent. Well, I mean, there's only one correct answer when you're in this building, right? All right. So, we're going to talk all things ANs, and Willie is going to have a wealth of knowledge and information that he's able to bring to the table. And I think ANs is one of those molecules which people may be aware of, but don't know the details, exactly what it's for, the applications, the history behind that. So we're going to get into all of that stuff today. So maybe Willie, could you please first explain what your role is in King and what it is that you do in this building?
Yeah, sure. Thanks, Rafe. First of all, thanks for coming. Great to have you here. Yeah. And, we watch your videos online. Always excited to hear it and know that you're a big fan of Alkylated Naphthalene. So glad you're able to join us, and thanks for having me. And, I started King possibly 22 years ago, actually as a pilot plant engineer, where we were just starting to develop the Alkylated Naphthalene technology, producing it here at King Industries. So I had a ground level start. We played around with different, mole ratios of, naphthalene and olefins, different catalyst systems. So we came up with our product line. And then from there, we developed it into a business now that is growing, that we're actually building a new facility, which is going to increase our capacity by 5 or 6 times. So we're excited about it. Alkylated naphthalenes, when I first came here, knowing how to make them versus how they're used is a transition. But, we see the market and the industry trending, more towards synthetic. And that's where the alkylated naphthalenes, as fit in. They help improve the, from oxidative stability, the solvency performance, different attributes that they provide to especially group 3s and PAOs.
Awesome. So maybe just to start, because I think a lot of people may not even be aware of what an alkylated naphthalene is. Right? So you already mentioned naphthalene, you mentioned olefins. So can we kind of combine all of these together and give a description for what exactly is this molecule?
Yeah, no, sure. We take naphthalene, which, most people know as mothballs, people have it in their house. And then we take different chain length olefins, and then we attach it to the naphthalene, and you get different substitutions. You get, mono being one olefin attached, and then you get di, tri, and tetra. And the way you choose what catalyst system you use and the chain length of the olefin, you get different properties. We become, through a lot of testing and pilot plant development, we've narrowed it down to, our current product line that we see gives the best performance depending on the viscosity grade and the requirements.
So if I were to compare it to some other base oils, right, you'd say it's not like a PAO in the sense that with a PAO, you're really just extending the size of the molecule, right? It's a polymerization reaction. You make something bigger or smaller depending on what kind of viscosity you want. This is maybe a little bit more akin to an ester, right? Where with an ester, you've got that sort of core functional group, and then depending on the direction of the functional group and sort of what we attach to it, you can get different properties out of it. Is that similar with the ANs?
In the sense of what some of the benefits esters can bring, it can bring solvency, performance, lubricity, being a more polar, they have better solubility properties. So when you look at your current base oils out there in the market, years ago, 30, 40 years ago, group 1 was the main one. And group 1 had, maybe not the best thermal oxidative performance, but it had good solvency. Why? Because it wasn't as refined. So it had the goodies in there, the cyclics, the aromatics, So then as time moved on and they saw that refining base oils further along provided better attributes, you had your group 2s and group 3s. And then, as you mentioned, the PAOs, definitely improved the oxidative stability, but you lost some of the solvency benefits. And, being an aromatic, different than an ester, we bring the solvency properties with that direction, where the esters are being a polar molecule. So they're bringing that benefit in a different manner. So there's some similarities in that aspect, but when it comes to certain performance attributes, the alkylated naphthalenes, I think, are clearly better choice.
So maybe you've gotten into a little bit of very minor bit of history there. So, you already mentioned working on the development of ANs early on in your career and things like that. So would you mind just kind of taking us back to, like, how do we develop these molecules? Where do we come from? How do we even figure out that they would be maybe appropriate for use in lubricants?
Well, a lot of times, I think really after World War II, you had the, you know, generation of, jet turbines, machinery that was running at higher temperature, more severe requirements. So, esters were used initially, and they're still used for jet engines because you need that thermal stability and performance and the lubricity they bring. But then alkylated naphthalenes in the 50s were started, as a synthetic lubricant. And, like any project that started, once they developed them, they saw the benefits of it. At that time, the market really wasn't ready for them because you were still predominantly, group 2. So you had this base stock that could do things at high temperatures, thermal stability, and provide those other benefits. But in the marketplace at that time, the other lubricants were still meeting the requirements, and the group 3s and 4s really weren't that present at that time. And over time, once the PAO market, group 3s really in the late 80s, early 90s started to come, then you really saw that the alkylated naphthalene started finding a home as a base oil modifier. So improving the properties of your group 3s, group 4s, and in some cases group 2, depending on the application. And, and also being used with esters in certain applications to produce, provide better volatility performance, like in chain loops, high temperature chain loops.
So it's a group 5, right?
Group 5, yeah.
Okay, so we're kind of, the way the API-based oxy groups are constructed. So unfortunately, group 5 is like that catch-all term.
The other ones, yeah.
Yeah. So for anyone who doesn't know already, but I think that's most of the people that listen to this podcast, obviously group 1 through to 3, that's the mineral oils. For some reason, PAO gets to be its own special boy.
Its own slot, yeah.
It gets its own little group, and then everyone else gets kind of lumped into group 5. And that ranges everything from extremely high performance, alkylated naphthalenes, polyphenol ethers, all that sort of stuff, right through to vegetable oils, right?
Yeah.
And
that's tags,
yeah.
Those other ones, yeah.
Okay. So now we've kind of got a bit of a background on like what the molecule is and where it comes from. What are the kinds of properties that I would expect just purely of an alkylated naphthalene? You already mentioned something like solvency and really good stability, but what about that molecule kind of gives it those properties?
Well, the naphthalene being aromatic, and then you have the olefin attached to it, but you have no functional groups. So sort of that's what makes base oil pretty stable too, because they're linear carbon chains. So there's nothing really that can get attacked unless heat breaks the bonds. So in this case, similar to us, we don't have that any functional groups, but because they're aromatic, the bonds are much more stronger. So these applications where they perform is we see it in longer lasting fluids, high temperature, and when you look at your base stocks that perform well. I mean, what they've done with PAOs, group 3s, group 2s, but they don't have, like I said, some of those goodies that the group 1 had, the solvency properties. So the molecule itself, when you compare it to like a mineral oil, group 2, group 3, and a PAO, from just say testing at like RPBOT, you're going to see, performance be 3 or 4 times better, as far as minutes, depending on which alkylated naphthalene you pick. The lower viscosity with the higher mono content is going to give you better oxidative performance, where the higher molecular weight with the di, tri, and tetra are going to give you better thermal stability and volatility performance. But
so just so I can stop you there, so we can make sure everyone's on the same page. When you talk about mono, di, tri, what exactly are you talking about? If we pictured the molecule?
Yeah. So if you see like you have the naphthalene ring, and then if you have just one olefin on it, that's a mono. And then once you put 2 on it, then now it's a di, 3, tri, tetra. Now there's a certain limit because of steric hindrance and stuff. Every one of the naphthalene carbons doesn't get olefin. There's a certain point where it stops. But overall, and we control that with our unique process. So we're able to dial in what we want as we see as the properties that give the best performance. And again, like I said, being in a pilot plant, we did a lot of trial and error with different stoichiometry relationships of the naphthalene and olefin to get the properties we wanted.
Hmm. Okay. So then we talked about that sort of like the stability of the bond. So the fact that it doesn't have functional groups. So I guess in the ester, that's sort of like the carbon double bonded to the oxygen, single bonded to another oxygen, right? Is that sort of functional group. We don't have that in an AN, which makes it inherently stable. Plus, you've also mentioned that the aromatic groups are also inherently stable. Another thing that you mentioned is like solvency as well. So if I were to compare it, like let's say, for example, you've got, in terms of solvencies on base oils, you've got, PAOs sit on one end, very low solvency. And then probably on the other end, you've got your oil soluble PAGs, right, that sit kind of at the other extreme. Esters are sort of somewhere in the middle. Where would an AN sit in that sort of?
Yeah, we sort of see it as, you have your mineral oils, PAO, your group twos, group threes, like you said, on the, say, the side of it where they don't have the great solvency properties. And then you say your esters over here with your PAGs, and then you have your alkylated naphthalenes, sort of not in the halfway point, but a little bit closer to the ester side, further away from the mineral oil as far as solvency performance. So there's some benefits with that. They're not as surface competitive as esters, so some advantages. And again, depending on the formulation, there's a clear advantage to using the alkylated naphthalenes versus an ester.
So that then brings us to, we've talked about the raw material properties just of an AN, but when you start to put it in formulations, let's say, for example, you just talked about competition on metal surfaces. So why is it an advantage that it would be less competitive?
Well, in some cases, because the ester itself wants to go to the surface, but you'll want additives to go to the surface.
Yeah.
This is the corrosion, additives, your anti-wear, surface active additives. So there's a balance there. And as the life of the lubricants gets consumed, more additives go to the surface, but those other additives still have to find their way. So as time goes on, the longer you compete against the ester, the less, the statistically, whatever that probability is, we see some advantage with the AN because they're not necessarily competing with the surface like the esters are. So it's that balance. We like to think we're in that sweet spot where you're going to get the solvency properties you need, but you're not going to really compete with the additives as much as the esters do.
Okay. And I guess, with esters being somewhat prone to hydrolysis as well, do you, how does water interact with an AN?
Yeah. So, well, water doesn't. It really doesn't affect ANs. And when you correctly brought up, when you look at compressors or certain, industrial applications to your oils where say you're getting water contamination, every lubricant has a certain lifetime. You got the additives, you got your base oil, and then you got your co-base stock. And let's just say in this case, you have an ester. So you have your ester over time breaking down, generating acid value. Your additives also are, prone to over time to break down and generate different species. So now you have these two things in your formulation that are breaking down at different rates, but they're breaking down. Well, pull the ester out, put the AN, now the AN's not breaking down. So that one factor you took away. And so when you're talking about fluids where you're trying to get that long life, extended life, you removed one component. Because one thing about lubricants, you measure acid value, which leads you to understand that the formulation is breaking down. But you don't want the viscosity to change because that's like the critical point. So if you wait too long and you see your acid value changing, but you don't respond until your viscosity changes, well, now that's going to lead to equipment failure because all the equipment's designed to perform at a certain viscosity. So acid value is a good indicator of oil breaking down, but you want to stop that viscosity change. So going back to the ester with additives, now that component of the alkylated naphthalenes is not going to be affecting that. It's not going to change the viscosity. It's not going to break down. So that's where we see, benefits. And it's, proven with our customers. We see them once they make that change, they see the benefits.
Okay. So that's kind of like what ANs give you in your formulation. So what are typical formulations that you would see alkylated naphthalenes in?
Yeah, so predominantly for us, the marketplace is broken up into, that we have the grease market, you have your industrial lubricants, and you have your high temperature chain fluids. So those are three markets we see. There's also the automotive side, which we get involved with in certain companies involving racing. But from our end, because we're more focused on the higher viscosity alkylated naphthalenes, the ones that are like 120 centistoke to 170, 180 at 40C, versus a lower viscosity one like 35, which we do offer. But from our end, we push more the higher viscosity. And what we see the benefits is in high temperature chain oils is reduced volatility. They're usually combined with esters, high temperature esters. We see a great improvement in reducing the volatility of the formulation, which helps the people use a lubricant use less of it because it's not volatilizing off, and they don't have to wet the chain as often. This is because you want to keep the chain wet, but you don't want to make it too wet because then you start building up varnish. And that's one thing nice about the alkylated naphthalene too. At high temperatures, it disassociates. So you have the olefin breaking off from the naphthalene ring and just flashing off, versus with esters or other mineral spirit or other mineral oil based stocks, including PAO, they can start either breaking up into fragments, which can lead to varnish, or, like esters, they can start pulverizing, which can lead to varnish. The other market we see ourselves in greases, because in greases we see that when people modify their grease formulations, were anywhere from 20 to 30, 40% of our KR. They see improved yields, improved work stability. So there's a clear benefit. They see that much smoother grease, which, if you think about a smoother grease, better surface contact. So, and then obviously with, we didn't mention before, but they have great response to antioxidants. So because of that, it just improves the life of the grease or any formulation. Compressors, screw compressors is a market that we're seeing more and more application in. These screw compressors have really taken the market over in the last 20 years on the reciprocal side. And those, because they're so tight, they're typically ashless. So ashless formulations don't have the benefit of having a zinc phosphate in it, which can be an anti-wear as well as a secondary antioxidant to the extent of life. So these need a fair amount of high treat of antioxidants, which, as I mentioned, they extend the life of the alkylated naphthalene further. So in these ashless formulations where you're running at 200 degrees, that's really where the alkylated naps shine. So these things are used out in fracking things. You got these big machines out there sucking in air, dirt. So that you want an oil that's not going to break down, because you already have things coming into it. A lot of water. They separate water well, and they won't hydrolyze. So that's an area. And then gear oils is another area we see the benefits of, just because the treat rate of additives is a little higher than you see versus, say, a compressor or hydraulic. Those can range from like 0.6 to tops, maybe 2%, where gear oils, you tend to see that 3 to 5% additive treat rate. So helps, especially in your more base stocks like PAO. Group 3s, you don't see gear oil so much because the viscosity is limited to like 68 centistoke. So, but that benefit, and then the benefit is too, as time goes on, as things break down, that solvency benefit helps too. Because when things break down, you want to keep them solubilized. You don't want them falling out as varnish. So there's multiple benefits for alkylated naphthalenes. We see in the marketplace, once we have customers who formulate it and supply their customers, there's nothing but positive things they say, and they really don't switch out of it. It's been and like I said, since I joined King, it's been a growth that's been pretty linear up, and I expect it to continue because I think the market's going to shift more and more towards the synthetic.
So, I mean, probably the only thing which is kind of not a black mark necessarily, but where traditionally people have desired, for example, a high viscosity index, right? That's probably the one area where ANs probably don't match up, right, to, let's say, for example, like your esters and your sort of your PAOs. But I guess if you're using it at relatively low treat rates, and especially in industrial formulations where VI is not really that important,
Right.
It's probably kind of like ideally suited to most of the applications that you're talking about, right?
Yeah, we see, overall, most of the people who formulated with it are using it, globally.
Yeah.
And one thing about alkylated naphthalenes, they do respond well to VIs. So you can prove it with the correct VI.
Yeah, right.
So, that's not really been, I think, a challenge for us. Because again, you hit on it, mostly it's because the treat rate tends to be in that range where it's not really, it might drop a pour point of a PAO from -48 or something to -44.
Okay.
Now, sometimes that might be a showstopper, but
yeah,
a lot of cases it's not.
Rare.
Yeah.
So maybe one other thing is just that, you've described the structure as looking like very much an aromatic, right? So it's effectively what two benzene rings kind of stuck together mix the naphthalene, which I'm no organic chemist, right? But in my conception of it, that looks pretty similar to a lot of the antioxidants that we use in formulations. Do you get any inherent And, well, one of the other things that you mentioned is the RPVOT value can be quite high of a neat AN.
Mm-hmm.
Do you get antioxidancy just by adding AN?
It's not in the sense of when you look at a typical like a minic or phenolic, which is really a scavenger of the free radical. So they're not going to scavenge free radicals, but they're not going to generate a lot of free radicals.
Okay.
Especially at certain temperatures. And you see that in PDSC data. You don't see them break down. You see in RPVOT testing. So because they're, the aromatic itself and those stronger bonds, the generation of free radicals is much less than you see in other base stocks. So that end, when you have a formulation with antioxidants, only a certain percentage is needed at at certain temperatures to keep the free radical generation in the alkylated naphthalene. That leaves most of that antioxidant available for the other parts of the formulation.
So that's what you were talking about when you said it had a really good response
Yeah.
to antioxidants.
Yeah, okay, that makes, because it's not generating as much as a free radical as a PAO. Like you could put 0.2% in a PAO, say 8 and 0.2% in our 0.15, and you'll see like 900 minutes in ours versus say 200 tops, 250.
Yeah.
And that's just because that antioxidant is not being consumed as fast because not as many free radicals are being generated.
Huh. Interesting. So, we've talked a lot about kind of what the molecule is, the typical applications where you'd see it. So where do you think kind of the future lies in the molecule, right? So, if I had to point to some, let's say, overarching trends in the industry, I think we already said at the very top of the discussion, everyone is slowly, our industry moves slowly, right?
Mm-hmm.
But everyone is slowly moving in the direction of synthetics. So that's probably in favor of ANs being used in more formulations. Do you see any, let's say, for example, either applications or lubricant types where ANs are not currently in use, but you could see them being beneficial?
Yeah, I think when you look at the market, like I said, we're, currently in gear oils, compressors, high temperature chain loops. The one area maybe is hydraulics. Over time, as they develop the new, systems over time, the more tighter tolerances develop, the more things run hotter. It's just, and whether that time frame is 5, 10, 15 years, industry is always headed. If you just look back from manufacturing of cars, how much tighter your engine is today, how much more violent it is, with the air, the turbos, and you get 4 cylinders now. Like back in my day, if you had 300 horsepower, it's like, woo, now 300 horsepower is your standard, BMW, 3 series, So what are they doing? They're taking essentially that same smaller engine actually, per liter and getting more out of it. So what are they doing? They're running it faster, hotter. So industry keeps working that way. So I think it's just a matter of, what's the next application where, hey, we see we can get more production out of this unit. And okay, that lubricant's it's going to require more demanding lubricant. So, from the current ones we think of, which is, like I said, gear oils, hydraulics, compressors, turbines, there'll be something else that comes along, whether it's these robots that they want to work faster. Like I said, the high temperature chain loop part has been something that we, been seeing amazing growth in. And just because, these, production is, how do you get it out? You run hotter, run faster. So
Yeah.
that's the trend, and then longer life, which is the next part. When they talk about carbon footprint, there's a part where you want to reduce your carbon footprint to, reducing your emissions, using things that are biodegradable or renewable. But there's also a part that we think of is, hey, if you have a factory that you're changing fluids out every 3 months and you're using, say, just picking up 50,000 gallons of fluid, but now you're only changing it out every 9 months. You're reducing your carbon footprint through waste and not use, and plus you're reducing downtime. And that's really been the trend. Me as a car owner, changed my oil when I was younger at 3,000 miles. I still change my oil, but now instead of changing every 3,000, which is roughly every 3-4 months, now I'm changing it maybe every 9 months. I like that. Not that I don't mind changing my oil, but it's less work.
Yeah.
So look at factories, same way, when they don't have to shut down to change over, that's a benefit for them. Because, everything's at the end, it's all about who's going to make that better mousetrap. And, if you're a person who's in the industry, whether you have a compressor, gearbox, hydraulics, downtime is lost time, whether it's changeover fluid or breakdown because you didn't use the correct lubricant. And, one thing at Kin, with the test equipment we have and other things that you'd see, we can help companies formulate, achieve these lubricants that not only meet the current standards of the oil, but can surpass them.
Yep. Yeah. Interesting. So, I mean, just something to add on there in terms of future applications. So, for anyone who's seen a couple of videos on the bright stock replacements, so I know the people that I work with that are looking forward to ExxonMobil coming out with their EHC 340 Max, right? And using that as a bright stock replacement. When you do that, come and see me, because I can almost guarantee that when you switch from the group 1 to the group 2, you'll start having deposit issues. And I think, for my clients, at least, I see, this as being a bit of a solution to that in some of the heavier hydraulic oils, as well as the heavy gear oils that we're going to start to see 340 Max in, because the same varnish issues where we went from group 1 to group 2 turbine oils, and all of a sudden we started producing all of these deposits. I think you're going to see exactly the same evolution, but for a whole raft of different products. So, don't speak to me when you have problems.
No, I agree with you. There's some changes you can't foresee, but they're going to happen. Changes, continues to happen, and anything that moves needs a lubricant, and it's just a matter, what conditions that lubricant needs to be used at, and that's where the alkylated naphthalenes are definitely, they're going to find that mark, because, like you said, things, we talked about things are running hotter. They want them to last longer, and that's like the ideal fit for these alkylated naphthalenes. So, and like you said, that trend, I agree with you 100%. You're going to need something to help solubilize that additives.
Cool. Well, hey, Willie, really appreciate you coming to talk about my favorite base oil. So I am very, 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 very partial to it, and have always really liked it in a couple of products that I've tended to use with customers. So yeah, really appreciate getting that sort of like insight into what is kind of like the mystery base oil. I think it's one that people have heard about but don't know a lot about. So yeah, really appreciate your time. And if anyone needs to know anything about it, come see Willie.
Yep. Please look forward to it.